Hi, I think I can see only one student, right? Uddars, you are there. So can you, am I audible to you, Uddars?
Yes, ma'am.
Okay, very good.
I
Okay.
can ask if they are coming.
Sorry, say that once again.
I can ask them on WhatsApp if they are coming.
Okay, okay. Sure, sure, sure. Please ask them. We can wait for 2 minutes, but not more because anyway, it is already five, right? 5 minutes I have waited. Okay, um, so do you have any question from last class? Whatever we have discussed
No, ma'am.
before? No, right? Okay, then maybe so you have understood how CPU is that useful resource is managed by operating system, right? That we discussed in earlier classes. So today we are going to move on to next resource means memory. So memory is another useful resource, and of course, I mean you need to manage the memory efficiently, right? So this we will learn from today onwards. Okay. So in the last few classes, you saw how operating system virtualizes the process or virtualizes the CPU, right? Mainly by creating the abstraction called process, right? So now we are going to see how to abstract memory. Okay. So first, so let us see the earliest system, right? So if you attended the first lecture, so there actually we discussed that in the early days system, uh, all the I mean, so you have a huge maybe the machines were also very big, so huge machines were used to be there, and one process at a time you could actually run over them, right? So if you want to implement that kind of system, I mean environment, right? So designing one operating system is very, I mean, it's a simple job, right? So in other words, you have just one process which you want to run over your system. So the memory, whatever you are going to take, that is actually that would be occupied by that process itself. So right. So if you see the memory, so let's say this is my RAM. So this is the physical memory, right? Some part of that memory is already occupied by operating system, right? So if some new process is coming into the picture, then basically the remaining free memory, whatever you have, the whole part of memory, one can dedicate it to the process. If in the process, I mean in the system, you have only one process to run, right? Right. So this is very simple environment. So and writing operating system and or managing memory is not that much tedious job if that is the system which you are looking at, right? So in other words, operating system which contains is code, data, right? Other parts, all the things which is actually loaded some part of the memory, physical memory, RAM, and the remaining part is dedicated to process one process itself, right? We have just one process. So if you remember, that process has code part, right? Code, then data, stack, heap, that those are the memory related to your process, right? So all those parts are actually stored over here, and you don't have to do anything fancy, yeah, right? So once this and during those early system, basically users didn't expect much from the operating system. Okay, so that was very easy days, right? Good. So if some process is new process is coming, you know that the old process should be dead, right? So there is no fancy thing. You can implement it very easily, right? Just you need to remember what is the starting address location for a process. That's it. Then the whole memory, remaining part of the memory is dedicated to the process. Very good. Now the problems become complex when basically we have multi-programming environment, right? So we realize that machines are very much expensive, and it is actually wise to be shared by many processes or many users, right? Multi-programming and time sharing system, right? So now the thing is basically once you also saw in the last few classes we discussed. So time sharing means if you have a process, it might happen that the process is running into your system, right? It is actually run by the CPU. Now you can actually time share the CPU, means you can just halt the process right at its present state, and you can take other process into the picture, right? So that's the thing. So if you want to implement that, then of course now if you have only one physical memory, right, similar to CPU, uh, question is how you can implement such time sharing environment, right? How you can utilize your memory efficiently? That's the question, right? So here is maybe one answer. So for example, let's say I have many processes are there. So similar to CPU management, let's do the same thing for memory management. Means whenever you want to context switch between processes, so what we can do, so this is the physical memory, means RAM. It's what is, I mean, the efficient one, right? That memory size is small, right? So what you can do, maybe, okay, I have one process which is running, right? So that now the memory, this part of the memory is basically, let's say, dedicated to the one process. Similar way you have actually managed your CPU. Now when you need to context switch between two processes, right? So then you can actually, maybe what you decide, let's swap out all these memory, which, right, corresponding to that process which you want to context switch from, right, to new process, and replace it by the other process. So means you want to swap this whole, maybe you can actually swap it out from the physical memory to some slower version of memory, for example, hard disk and all, right? In disk, you just remember all this, you just swap it out into slower memory, right? So that's one option you can do. Similarly, basically, for the new process which you want to run now, right? So for that process, of course, the all the things whatever you have corresponding to that process, let's say it was actually stored in the hard disk. So you just swap it from, or maybe just copy it from the hard disk to your physical memory, right? So that's one approach, or maybe I should say easy approach to implement this time sharing thing, right? Or multi-programming environment, right? I hope you have understood this approach. Can you just tell me, if I am going to apply this approach or maybe implement this approach, then what are the problems you are going to face? Can you tell me? I hope you have understood it. Did you understand this? You didn't understand. Okay, so one, of course, the main problem is actually it is going to be slow, right? Why this is going to be slow? Uddharsh, you are saying something. I didn't.
Yes, ma'am. From there to
Yes.
the people who have joined.
Okay, good. So I can see two other people. Yes. Okay, but did you get my question? So are you? Do you want to answer my question? No, right? Okay. So and are you with me? So far I have just discussed one simple approach to implement the multi sharing environment, right? So the approach is very simple and straightforward, and the obvious problem is basically it is going to be slow. Why it is going to be slow? Because basically what you are going to do here, you are swapping the whole memory, right, occupied by one process, that you are going to swap it out from the physical memory to some slower memory, and memory access is basically very slow process. Okay, it's not like you are actually, it's not like changing some register. It's not like that. Registers are actually very fast, okay, compared to memory. Physical memory means RAM. Okay, so that's why it is very slow approach, and it's not recommended at all. Okay, the simple approach which I just discussed. Okay, so that's the point, because So if you think that okay, the similar we actually did the similar thing when we manage CPU, right? We actually swap out the process from the CPU and we dedicated the CPU to some other process. So we actually applied the same approach over here to manage the memory, but it turns out to be very slow and it's not practical in fact. Okay. Okay, very good. Right. So the main reason is saving the entire content of memory to disk is a slow process. It's a brutally non-performant. Okay, very good. So now the question is, what could be your remedy, right? What kind of thing you can actually, if you want to, I mean, look for some alternative approach, then if you understood, so I should not remove the whole memory space occupied by the process to the slower memory when we are going to context switch. So rather, we should actually leave that part of the memory in your physical memory itself. Okay, we should not remove it, right? So that's the alternate approach. Leave the process in memory while switching between them. So in other words, so since we are going to do this, so in other words, we are saying that okay, it's not the case that apart from operating system, whatever operating system of course is taking some part of your physical memory. So the remaining part of the physical memory, we are not going to dedicate to one particular process. Rather, we are actually going to share this physical memory. Means we are actually many processes at a time I mean, they are actually going to access the physical memory. Or maybe, in other words, the same physical memory, right? That physical memory is partitioned among many processes, right? Okay, so that's the remaining. Okay, so now basically, if you want to implement such thing, right? So the thing which I just mentioned, uh, mm, so there should be, if you, so of course it is not so simple. So, but if you are going to implement such thing, some of the aspect you should also take care. For example, it should not be the case that user means the programmer they should feel messy, right? For example, I should not care about where this particular code is written over there, right? In which part of the things, right? So we should hide this complexity, right? This how the things is happening over in the underlying thing, right? So to do that, basically we need to virtualize our memory, right? So since many processes are actually are accessing the memory, right? And it might happen that for a particular process, the all the memory whatever we need to actually give to the process, it might not be, they might not be in a contiguous memory at all, right? They might be some part of code, maybe somewhere. Say, let's say this is my all physical memory. So for process one, the code is over here. This is the code corresponding to process one, and the maybe the stack part is stored somewhere else. Okay, right. So, but so this is too much complex, right? For which part is going over where, right? So, but the user should not feel that this is too much complex thing. Rather, the programmer should, I mean, they should have the feeling that okay, uh, as if my whole physical memory is going to be dedicated to my process. It starts from zero and to some number of, I mean, address space, depending upon how big your program is, right? Something like that. So right, so this kind of virtualization. So if you want to do, then basically you need to write a good operating system, right? So which will hide this complex thing from the user, and it will give the impression to the user that okay, so my address space is going to start from zero location of the memory and some particular part of the memory, and maybe the whole memory is actually dedicated to my process, right? We hardly bother about how much space we are going to use, our process is going to use, right? So right, okay, so in other words, so so in other words, so if you understood, so as I mentioned, as if user understood that okay, my address space, it starts from zero, right, and it ends at some part of the time, right? So whichever this address space which actually users are actually aware about, these are basically not exact physical address, right? So if you have the physical memory, so there the whatever the exact physical address that is not given to the user. User are not you will not be able to get you will not be able to access where that address is, where my data is going to be stored. So that is completely hidden from the user. Okay, so of course the one reason for hiding is basically if the user can know that okay, my this is dedicated to this, some space is dedicated for me. So okay, I can actually, they can do something else right over there. They can change something or do something illegal thing also. And another important thing is basically, this is one thing. Another thing is that's too much complex. That address space of a physical memory, that's a huge number, right? So why should I give you? I mean, why should I know that number? Why should I give that exact address space to the user, right? So in other words, if you ever written some program, for example, let's say I have written some program like this, so which prints basically the address location. For example, the address location where the main starts. Okay, so that location, if you want to print, so you can actually always print out this. But the address location which will be printed if you just run this program, these address are basically virtual address. They are not physical address. Okay. But there should be some mechanism, right? In other words, this CPU actually, whatever CPU issues some loads, right, or stores, that address, whatever the CPU issues, those are nothing but virtual address. They are not the actual physical address. Okay, but there is some hardware. Okay, so which is actually responsible to convert this virtual address to the correct physical address. Okay, so there should be some hardware help. So for example, this is the virtual address space corresponding to a process, right? And for example, code, right? The code part is actually broken down into maybe several parts. For example, code is here, one part of code, another part of code is stored over here, right? So now, if CPU fetches some instruction, for example, for some virtual address location over here, right? So CPU also doesn't bother about from which part of the, I mean, physical address it is coming. So it will just give the virtual address location, right? And we have one hardware. So we'll discuss in detail which kind of hardware support you should have, so that given any virtual address, it can actually translate it into physical address, and it can actually correctly go to that instruction which is actually stored over the CPU. Sorry, not CPU, over the physical memory, and it can fetch it, okay, and run it over the CPU. Okay, so basically, if you understand, in last part of our discussion, means not today's discussion, last part of our course. So when we discussed about virtualizing CPU, right? So then we discussed that operating system developer always needs some help from hardware, right? So for example, we need help in terms of mode bit, right? We needed help for in timer interrupt, right? Those are all help from the hardware. Those are needed, right? Similarly, here also, when we'll manage memory, then we'll see several hardware requirements will come into the picture. Okay, so one such example is memory management, right? So if you want to translate the memory virtual address to physical address, exact physical address, so there should be some hardware support for that. Okay, it depends upon how you are going to implement or how you are going to handle your memory, right? Okay, very good. I hope you have understood at least the if you want to manage your memory, right? So there should be some goal, right? For example, when we manage our CPU, then also we had some goal. We listed out our goals. So here, if you are going to implement, I mean, if you are going to manage your memory, right, efficiently, then the criteria, or the objective should be the system should be transparent, right? So transparency in the sense the user should not be, aware about the messy details where your program is going to be stored, right? So this kind of hiding we are referring as transparency, right? Though in real thing this is not transparent because the user doesn't know about the real location where it is going to be stored. Rather, it is hidden from the user. Okay, so this is one objective. First objective is basically user should not. We should not user programs. They should not be. They should not feel that this is too much complex thing where this code is going to be stored. So depending upon that, maybe I need to write my code. Might need to change my program, something like that. This kind of feeling they should not have. Right. This is the first objective, I should say. And the second most important objective is efficiency. Means, as you mentioned, right? So first we gave you one approach, simple approach, where we just said, okay, whole memory is dedicated to a process. So whenever a new process, or maybe we want to context switch between processes, we can swap out the memory to the slower memory hard disk, right? And we can swap in the process which we would like to execute, right? So this, if you want to apply that simple mechanism, then that mechanism is basically it is going to make your system inefficient, right? It's not at all efficient, right? So there is so much overhead by moving whole chunk of memory from physical memory to slower memory hard disk, right? So this overhead, of course, you should minimize, right? That is basically another objective if you want to implement or if you want to manage your memory efficiently, right? And another primary objective is basically you should it should not be the case that you are wasting your memory also, right? It should not be the case, right? So for example, let's say in your memory, in the physical memory, there are several chunks which are actually free, but it might happen that you are not able to run your new process because you are running out of memory for some reason. You are saying that, so this is in other sense wastage of memory, right? So that kind of thing also should not be there. You should minimize that wastage of memory. So wastage of memory. So when you want to implement, you want to design your operating system, right? With the objective that you want to handle your memory efficiently, then you should also consider to minimize access time also, right? Memory access time and all, right? Because you need to, whenever you want to execute something or if you want to load something, then basically you need to access your memory, right? So these are all important goal parameter. Another third parameter is basically that is also important. It so as if you understood, so we have many processes to run, right? And all these processes are actually going to be stored in some part of your memory, right? And it is also the case that when the process is running, the process will also change some part of the physical memory, right? It will modify it, it will write something new data. So it should not be the case that one process is actually writing something which is actually disturbing some other process, right? Or it is actually changing some code part or maybe data or heap part or stack part of some other process. It should not be the case, right? So in other words, there should be each process, the address space of a process, right? That memory, whatever it is given to that process, that should be protected from other process, right? In other words, there should be some isolations between all those processes, right? So these are the basically goal which you should keep in your mind when you are going to virtualize your memory, right? Okay, I hope you have understood at least the objective of memory virtualization. Means what are the main objective when you are going to design your operating system from the perspective of memory management. I hope you have understood this. If you have any question, please raise your voice. If you have any question, please raise your voice. Do you have any question from this?
No, it's fine.
Okay, it's fine. Okay, it's very simple, right? Okay, good. Now let's. So as I said, there should be some mechanism, right, which will actually convert your virtual address to physical address, right? So that is known as address translation mechanism. So now we are going to discuss that in detail. So at least we are going to see uh, how you can actually convert one virtual address to a physical address. Okay, with one simple approach. So that simple approach. Okay, so with of course there would be some assumption also. If you remember in last class when we design scheduler. So initially, basically, we had a set of assumptions. We started from a set of assumptions, which are very simple assumptions, right? Because simplicity will sometime will make your life very easy. But so one after another, you need to actually remove those simple and unrealistic assumptions, right? So similarly, we'll start with a set of assumptions which are very simple. And if you assume those assumptions, maybe implementing this address translation mechanism would be easier for you. Okay. And we'll see, not in this class, maybe, right, so next class and next few class onwards, we'll see how you can lift those assumptions one after another. Okay. So we'll not talk about this in today's class, but next class onwards, we'll see that. Okay. Okay, so basically now we are going to answer these three questions. If you understood the memory management, okay, so sorry. So first of all, first question is how do we maintain control over which memory location an application can access, right? So for example, as I mentioned, there are many application or many user program. So now the question is how you are going to control that which memory location is actually going to be accessed by which process. Means you should not allow one process to access some other's memory, right? That I discussed just few minutes before, right? So how do you ensure these things, right? In other words, how to ensure the application memory access are properly restricted, right? So it's not the case that one process is actually accessing some other's memory, right? So how you are going to ensure it? These are the some of the question, right? And another question is how we can do this efficiently. Okay. So first, let's answer this question first. Then automatically you will get these answers one by one another. Okay. First, so instead of answering all these questions together, so first let us answer this question: how we can convert a virtual address space to a physical address space. As I said, that this is the main objective right now. Okay, we are going to convert one virtual address space to a physical address, right? And of course, as I said, there should be some hardware, right, which which is actually which will do the main part, means which will transform the virtual address to the physical address, right? And what is the task of operating system? So operating system also will be involved in the key point, right? Means, for example, so you need to initialize the hardware, this hardware which I'm talking about, right? You need to change some of the time the hardware, right? So those values will be fed by the operating system at key point. So that is the task of operating system. Okay. Okay, so as I said, so we are going to make a set of assumptions, which might, which are very simple assumptions. There is nothing wrong in it. So first, let us, okay, some of the assumptions are, as I said, might not be realistic. Okay, first, let us assume that the address space, whatever we are going to give, address space for each process, they are basically will be will be given in a contiguous part of the physical memory. So it should not be this case. For example, as I said here, the code part could be here, stack part could be somewhere else. Let's first make this simplistic assumption that for each process, whatever the memory space it is going to be required by that process, we are going to give that memory in a contiguous fashion. Okay, so that's the first assumption. And the second assumption is the size of each address space, right? So for each process, it's not too big, right? In other words, it is less than the size of the physical memory. Okay. So, but in real world, it might not be the case. It might be that my physical memory, that space is too small compared to the actual physical address. Sorry, actual the virtual address, whatever you have for a process. That address might be bigger compared to physical memory also, right? But for the time being, we are assuming that your address space for all the process, whatever you have in mind, so they have address. The size of the address space is less compared to the physical memory. And the third assumption is basically, it's also another simplistic assumption. What we are going to make is basically each address space for all, I mean, you have a set of process, right? We are assuming that all the process has same size of address space. So their address space are of same size. Okay. Okay. So if you have all these three assumptions, simplistic assumptions, okay. Now the question is, how can you manage your memory, right? How can you translate the virtual address into physical address, right? That's the question. So in other words, the picture would look like this, if you remember. I have, if you just apply these assumptions, so some part of the memory, this is the physical memory RAM I am talking about. So it is occupied by operating system. So let's say that is the beginning part, 0 to some part, right? So now the remaining part, basically, as I said, they are occupied contiguously by process. For example, this part is occupied by process 1. This part is, let's say, occupied by process 2, and this part is, let's say, process 3. They are all given contiguous manner, right? And the picture is basically, for example, process 0, P1, so its at virtual address space starts from 0, and let's say it ends over something, some address, let's say 1000 or something. Okay. But in reality, so it is actually, so let's say this is 0 and it is some M, it is, or maybe let's say this is B. So in reality, this 0 is mapped to here, right? Not in here, right? Right? Does the picture look something what you want to see? Okay. For example, here, let's say this is the process, right? Single process. So basically, this process, this whole process is actually the memory corresponding to the process is given to this part of the memory, right? So how can you, what should be your address translation mechanism? What kind of thing you should have if you want to uh, mm, so given any virtual address, for example, let's say the k is that virtual address, right? So how will you convert that virtual address to physical address? Can you tell me how you can do that? I hope you have understood it. If not, okay, hold on this question. Let us see some example. Okay, so to understand it more details means how, when and where you need this address translation mechanism. Okay, when you need this, address translation. For that, maybe you can have a look at this piece of code. Okay, so though this is written in C, so you can convert this in assembly language also. For example, let's say this is that assembly code corresponding to it. So what we do over here, so here basically we have one variable, right? So that variable value is increased by 3, right? So correspondingly, we have some assembly level code, right? So that code would be written somewhere, right? So let's say these are actually written at address location 128, right? So what it says that load x, right? X is that variable, whatever you have the value. So load that into some register, right? If you just convert this, it would be just 3 instruction unit. So load first whatever you have x, right, into some register, means in the CPU, right? Then add 3 to that register, right? So once this add is done, then basically move this register value to your memory, right? Right. So memory means here basically load this, right? So this address location you want to actually load back, right? Does it make sense? So if you just want to convert this line of code into assembly, then it has basically 3 instructions in assembly level. First you need to move that value of x into one physical, sorry, in register, which is a faster memory, right? It's in the CPU. Then you convert, I mean, you add 3 to that in that register, right? So then the whatever the resultant, whatever you obtain, then you want to write that result to your main memory, right? So if you see correspondingly in I mean what type of action we need to do, first you need to fetch. If you want to execute these 3 instructions, right? First thing which you need, basically you need to fetch instruction from this address. Okay, so this is here where you need address translation mechanism, right? So this 128 whatever we have, so that 128 is this line, basically it is not the actual physical address. This is basically virtual address, right? So you need to convert that virtual address into physical address, right? That's one, I mean, where you need that mechanism. Then after fetching the instruction, after fetching the instruction, you need to execute the instruction, right? So which actually, so execute the instruction means it's a move instruction. So which itself again it's a memory instruction, means you need to load from memory, right? And this memory is again it's basically it's a virtual address, right? Does it make sense? So these are the address. So have you ever written something some in assembly level? Have you written some code before? Has anyone, did anyone do this before? Assembly level code? No. So this is basically assembly level code. So you have some line, right? These are some line numbers. So, right. Yes.
I've written some lines in assembly.
You have written. Okay, good, very good. Then you may relate this thing basically. So basically, so these lines, right? These line numbers, whatever you have, this is basically address location. So these address are basically virtual. This is not the actual physical address, right? So now you can see the next instruction we need after doing this move instruction. Again, you need to fetch the instruction from here 132 this line, right? This, so again, so this address whatever from where 132, that address is actually virtual address. You need to convert that address into physical address, right? Once that is done, then you can execute the instruction, right? So this instruction, the second instruction, it is basically addition. So without using memory you can perform it, because this is just addition. So ALU will do that. Arithmetic logical unit will perform the operation without any memory reference. Okay. So once that is done, basically next instruction you need to fetch, right? So you know that PC is actually pointing to that, right? So that once you have fetched this instruction, this again you need one memory reference. So here basically you need to convert this address into your physical address, right? Then you can execute the instruction. And this execution of this third instruction itself, again, it is you have some memory reference, means you need to store, right, that register value to some address location, and this address location which the CPU knows, that address location is basically one address location of virtual address. It's not physical address, right? So in other words, whatever CPU sees, right, or CPU generates some address, those addresses are basically virtual address. They are not physical address. Okay. And those physical, I mean, from that virtual address, we should have some mechanism which will actually convert that virtual address to physical address, right? Okay. Okay. There is some power cut, I think. So that's not a problem. You will not be able to see me, but anyway, I can discuss all the things. So very good. Okay, so this is the picture, right? So in the with the simplistic assumption and all, so if you have assumed that whole address space of a process is allocated to contiguous part of your physical memory, right? Okay, so now the question is how how you can implement this thing, right? With the help of, as I mentioned, with the help of hardware, right? So here basically with some simple help of hardware we can implement it. We are going to use two registers, okay, base and bound registers, two registers. So one is actually responsible. So there should be some picture, yeah. So basically I have two registers like this. One is base register, another is bound register. So what I am going to store over there, so base register, in the base register basically I am going to store the starting location. So this starting location I am going to store for a process. So since I made the simplistic assumption that the whole physical memory, whole address space of a process is going to be stored in a contiguous part of a memory. So if I just remember this base address, means the starting address of that part of the memory, then that would be enough for me, right? If I just, you need to just add, given any virtual address k, right? If you just add k with this base address, then you will be able to get back to the exact physical address, right? There is no problem, right? Does it make sense to you? First of all, can you hear me? There was some power cut.
Yes, ma'am. Yes,
So,
ma'am.
okay, good. So, do you understand this, right?
Yes,
So
ma'am.
the question, acha, so okay, very good. So now if I have just this base one register, let's call that base register, then that is enough for me, right? Now the question is, if you have such thing, then there is no restriction. The process can actually write anything. For example, it will just enumerate some address location, and with that add it to the base address. Then it can actually go and jump to some other location, right? There should be some restriction, right? So if you want to restrict your process so that it do not access others' memory, then you should have some base. With base register, we should have something called bound register. Okay, so the picture looks like this. Okay, I'll just get back to my desktop because I think power is now back. Just a minute. Okay, I hope right, you can see me now. Okay, very good. So now the question is, I mean, as I mentioned, if I just have one register, then that is enough for me. But we want to restrict our process so that it don't disturb other process. It should not be able to read other process memory, right, or write something in other process memory. So to restrict that, we can have another register called bound register, right, where basically we can store this value, means for a process, let's say the total address space size is total 16 kb. So we can write the value 16 kb, means its virtual address start from 0 and ends at 16 kb, right? So it can write that value over the bound register, right? And now, if you see the picture looks like this. So when one process, so we have processor is actually generating this address, right, which are actually the virtual address. So once this virtual address is generated, we can just add that with that virtual address to the base register. So this is basically adder. Those of you know what is adder, this is just simple adder. Okay, this is again hardware. Okay, one hardware is responsible hardware which can add. So it will add the virtual address to the base address and it will generate the physical address. Okay, and then it can access whatever you want to access. And if, of course, at the same time, the generated address, virtual address, it will also check with the bound register. Okay, if you see that the bound whatever the virtual address it generated, the processor has generated, that address is basically it's bigger than 16 KB, for example. It is beyond your virtual address space. Then operating system actually, so this hardware they should raise some exception, right? They should give some exception, and operating system should do something, right? Operating system should take care of something at this moment. Okay, does it make sense? Okay, I hope you have understood this base and bound approach, right? So if you see again from processor's point of view, as if so, if you see this messy details, right? It is processor is unaware about this. So processor is just one after another. It is creating some generating some virtual address, right? And those virtual address it is correctly actually taken care by this memory management unit, MMU. You have correctly hidden all these messy details from others, right? Right, a processor, as if processor sees that okay, he is going to generate virtual address one after another, and from those virtual address you are going to get data, or you are going to write something in that virtual address, right? But actually it is not. So this hardware with the help of operating system with the help of hardware, it is actually managing this in this way, right? So these messy details, though it's not that much messy, it is very simple here. Okay, very good. I hope you have understood this. Now I have one question. So is there any other way to implement bound register? So if you see the picture, so basically I'll remove all these things. So here basically we have drawn the bound register over here. So is there any other way to draw bound register? So is it the only way to implement base and bound, or there can be other ways also to implement anything? Let's say I want to implement this base and bound approach. I hope everybody understood the base and bound approach. There should not be any problem. Everybody understood it, right? So the question is it the only way we can implement base and bound, or there can be other ways also? There can be other ways also. So we can implement in other way also. For example, here we actually our bound register, we just fed bound register over here, right? So instead of doing that, we could actually do something like this. Okay, we have added anyway this base virtual address plus base we have added. So that physical address, let us check with the bound. You compare. So okay, I did not say that here we have a comparator. Okay, I did not say this, right? This is again another hardware. Those of you already have done some course on digital circuits and all, then those you know what is comparator, how to implement comparator using circuitry, right? Similarly, adder, right? Okay, so here basically with the help of comparator, we can check the bound register. So that I missed. We have a comparator over here. So we have basically two register, one adder and one comparator. Okay, so we can alternatively design the same thing to get the same result. So what is the thing which I am talking about? Instead of, so that is also very much straightforward. There is nothing fancy over here. So I have a process, right? So it is generating virtual address. Okay, so now you have adder. So you are adding this at this with the base register's address. So this is a base register. This is again, since this is a register, it's a very fast memory. Okay, so you are adding this virtual address with base register. Okay, then you just compare this value. So you compare this value with uh, bound register. Bound register. If you see that the bound is actually it is within the bound, then you access the memory. Otherwise, you just raise exception. Right? This is another alternative approach. I mean, it's same approach, just you have written the circuitry differently. So after adding, you are actually checking with the bound register. Of course, now the bound register value we should not fill with the last address location of the virtual address, right? We should actually fill up this location by the physical address, the actual physical address of the last So for a process, right, some part of the memory was allocated. So what is the last address location? So that you need to remember over there in that case. Okay, does it make sense? Does it make sense to you?
Yes, ma'am.
So this is okay, good. So this is very simple design, right? Where basically we have one adder, one comparator, one base registers, and bound registers. This is very fast also. Okay, it's too fast, very fast. Very good. Okay, now if you understood this, the picture, if you understood the picture, as I mentioned, of course, operating. So far, this was just hardware mechanism, right? We have base register, we have bound register, and I have adder and comparator, and this is this is processor, means CPU. It is generating the virtual address, and we have the physical memory over here, MMU. Sorry, physical memory, just RAM. Okay, so far, I mean, in this in this picture, operating system did not take any role, but operating system should involve somewhere, as I mentioned before, also, right? So it should take some responsibility. Now the question is, what are those critical points? As I mentioned, there are some key points when operating system should take responsibility so that this system is actually uh, it's running smoothly, right? So what are those critical juncture? So any idea about this? Of course, one juncture is when one process is created. Then of course operating system need to do something. Means it need to initialize that base and bound register. So what are the other times when operating system should do something, okay, in this environment? I hope that question makes sense to you. So far, whatever I just mentioned, that is just hardware, right? Now the question is, what are the critical moments when operating system should actively play some role? That is the question. Okay, if you want to implement this, right, this is just hardware. So whatever I mentioned so far, that is just hardware. Okay, so as I mentioned, one moment is basically when one process is, that's one moment. What are the other moments? Okay, other moments is obviously when one process is terminated, that then also we need to do something, right? So something we should do, right? And what else? Any idea? You're not talking to me this today, why? So another important thing is when context switch occurs, right? So these are the three main points when operating system should uh, do its important role. Okay, let us see one by one. Then only you will understand. So, for example, let's say one process is created. Then operating system should do something. So, what are the tasks of operating system? If you have this system, I hope you have understood this base and bound approach. So, which we are going to implement. Let's say. So now the question is, what are the tasks? I mean, what are the duties or responsibilities of operating system? Means what are the code you need to have? So when you want to implement such thing, okay, what are the code you need to write? Does it make sense? For example, when one process is created, what you should do? It's very simple, right? It's very simple. When one process is created, then basically the first thing you need to do is you need to find. So some part of the memory is already occupied by operating system, right? And some of the part of the memory is already occupied by some other process, right? So when one process is created, first thing operating system should do is basically it should find out one free space which it can allocate to the process, right? That is the first task it should do. The free space management, right? You need to find out the free space where you can allocate the process. So that's the first task. Let's say we have correctly operating system has some data structure it has, so that it can find out a free space. For example, this is one free space. Okay. Huh.
How do
Right.
we know what amount of free space is required for this particular task in advance?
Right. That's a good question. So if you are with me from the beginning, we mentioned that this is we have made some assumptions, right? We made the assumption that each of the process are of same size, right? So for example, so in that simplistic assumption, we take it for granted that all the process required same part of memory, I mean same size of memory, right? So in that case, we know that okay, that process, the process which we have created, so that is going to take some X amount of memory. So we are looking for X amount of free contiguous memory. Does it make sense, Akshay?
Okay,
This is
ma'am.
simplistic.
Yeah, for
This is
like,
right. So for the simplest, right, if the assumption we are playing, right, as I mentioned, these are all simplistic assumptions just to make sure that you understand what is the operating system role and all, right, if you are going to implement that. So these assumptions are very simplistic and sometimes not even realistic also. So we'll leave these assumptions one by one throughout our classes. Means not in this lecture, in next lecture, next lecture, we'll lift out some of the assumptions one by one. Okay. But with that simplistic assumption, you can understand that you should have some mechanism to find out free space, right? So there should be some data structure which is actually maintaining a list of free memory which is available to you, right? And once that free space is right, all right. So there should be some data structure. That's the first task, right? So once this free memory is actually found out, we found out, the operating system find out that this is the free memory available, then it should remember the base and bound of that process, right? Means base is basically this, and bound, if you are going to implement bound in this way, then the last address you should remember corresponding to that process in the proc structure. Okay, you are not going to change the base and bound of the physical, I mean, base and bound registered immediately, right? When one process is created, it might not be executed immediately, right? You just create it and make it ready, right? So does it make sense? So in other words, right? So it is actually OS must be able to allocate memory, right? And it should keep track of, which I already mentioned, a free list, right? So right, a free list should be there. So that those are the main tasks, right? When one process is created. So basically, when one process is created, operating system should find out one free memory which is available where you can allocate your process. Then basically, once that is found out, you allocate that part of the memory to the process, and you need to maintain this base and bound, right, in proc structure corresponding to each process. Okay, because we are assuming that the process is going to stay there unless and until it is dead, okay, in that memory, right? So that base and bound, whatever you have corresponding to each process, that value, there should be some way to remember, right? And that you are going to remember in the proc structure of the process. So if you remember, when we define process, right, in one of the class we defined data structure corresponding to each process, which is proc structure or PCB, which is right. So that, and I also mentioned that this the content of PCB will be keep changing depending upon your data structure. Now you can see the relevant, right? Okay, I hope you have understood this. Good. Okay, so as I mentioned already, so the first task is find a room for a new address space, and that you can find out from the free list, right? So this free list, again, we will discuss in one of the lecture, but how you can maintain this free list in detail. That you can actually think about. So this is nothing but a list you can maintain using linked list basically, right? You just remember the free space where it starts from, that address space, and how much memory is free that you can store, right, using a linked list. Okay, very good. There, it's not the only way. You can you can do something fancy data structure also. You can play with that. So this how to maintain this list and all. Okay, so that we will see in some of the lectures, upcoming lectures. We will see in detail. Okay, so good. So I hope you have understood the role of operating system when one process is created. Now the question is, when one process is terminated, which operating system should do something, right? There should be something we should do. So what do you think that what we should do when one process is terminated? Similarly, right? Right? Yes.
Free the
Akshay, you are right. So we need to free the space occupied by the memory. And how to do that? So what you are going to do? Are you free? What is the meaning of freeing here? So the freeing here is basically, as I mentioned, we are maintaining a free list, right? So there we are just going to add one node saying that this part of the memory is available with that much amount of memory. Okay. So freeing of memory is just doing this, right? We are not doing something fancy, or we are not writing that this is empty. Some values were taken, right? Maybe we are not doing that. Okay, make all of them 0, 0, 0. No, we are not doing this. Okay, because or something null, empty. That thing we are not doing. We are just in the free list. We are just adding one node saying that okay, that part of memory is actually free. Okay, that's the part basically. Right. So, for example, here, right, this process is, let's say, terminated. So now the free list, earlier the free list was this. Now you have added one extra node over this, corresponds to this, which is added in the free list. Okay, good. Now the third point, third critical point when operating system should do something is when context switch occurs, right? So when context switch occurs, can you say what are the important things operating system should do? I hope the picture is clear to you. We have just base and bound, and so CPU was actually executing one process, right? But context switch happened means that process need to be halted, right? And we should run to some different process, right? So if you want to do that, of course, you need to remember some part, right, corresponding to the running process which was running, right? So that is anyway base and bound register, so that you are going to remember into the proc structure of the process, right? So that you are going to remember what is the value of base and bound of the process which was running, right? That's one task. And another task is basically with addition to, to that you are going to do basically, you need to reset the base and bound register, right, with the value of base and bound for the process which you are about to run, right? Does it make sense? That's the only thing which you need to do, nothing else. Of course, context switch we discussed in detail in last class, right? So the low level mechanism details, whatever you have, that also of course you need to do. With addition to that, we need to remember the base and bound register, and we need to reload the base and bound register of the process which you are going to run, right? Does it make sense? I am not saying that this is the only thing you need to do. So it will be clear in more detail with some picture. Maybe I will show you one picture. Okay, right. So this was the picture for context switch. So this was the process which was running, right? And the base and bound register was occupied by this, right? Now, if you want to run some other process, then basically I need to change the base and bound register. So that should be loaded by the new base and bound value of the new, the process which you are going to run, right? And the base and bound of the old process you are going to store in the proc structure of the process. This process, the process is, let's say this is A and this is B. So the corresponding to PCB, I am going to store it. So this is the picture. Okay, another important thing. So again, if you go back to the picture I mentioned, so apart from this, there is another important time or another important event when operating system should play some role. I mentioned that. So that time is basically when there is some exception, right? Means your processor has generated some address, right? So that address is not in the bound, right? So in that case, there is some exception is raised, and in that time also operating system should do something. Okay, what operating system should do? Can you tell me? What do you think that operating system should do at this moment if some exception happened due to this? It's out of bound, right? So what operating system do for such kind of process? What do you think? Akshay, did you understand the question?
I want to know that when and when is the process creating the virtual address? Whenever the process is created, terminated, and context switching at that time?
Virtual address. Okay, virtual address, you see, so that's why I was telling you. So you have, so in general, you write some code. Nowadays, you are writing code in C, C++, Java, or somebody is writing in Python, right? But at the end, those codes are actually, if you compile them, then you create some executable, right? So those executable, what is that executable contains? It contains instruction, right?
Yes.
And those are basically assembly level instruction, low level code you have. So they have, so some part of this, so for example, that code is maybe it's written in the from 0 to some address, right? So they have some address that it starts from 0 to something, right? Those are address. That address is nothing but the virtual address. So that is the reason I asked I asked that you have written assembly level code at any point of your career sometime. So if you write assembly level code, sometime if you will realize that, for example, if you write C code, right? You jump to some location. So there basically we just mentioned the function name, right? But if you write that in assembly level code, you need to actually write the address where you need to give that jump, means where that code is written. So that is with that, I mean, that is a virtual address is actually whenever you are generating the executable, it's with that. You don't need to create, operating system will not create it. So it is automatically there. If you have executable, then the virtual address is already there. It starts from 0 and it ends to some space. Does it make sense?
Okay, so the processor, processor is creating the virtual address whenever it is encountering an executable. This is what you are saying.
Right. So that at least for the code part you have that, right? Now, if you are going to run that code in your machine, you additional to that code instruction, whatever that thing you have. Apart from that, you are actually giving that heap stack, right? So they are of course not in the executable, right? So whenever you are creating your process, right? So the operating system is allocating some part of your memory to the process, and in that in that physical memory, so you have some part for code, some part for stack, some part for heap. Okay, so these are all physical addresses, right?
Okay.
And correspondingly, so what is the virtual address we are talking about? The virtual address is basically those addresses which are generated by CPU. And if you see the address generated by CPU are actually the address from where you want to fetch the instruction, and from where you want to get some value, right? The data you want to fetch, and some address location where you want to load your data, right? Right? Does it make sense? So basically, those addresses are coming from code, data, part of your memory, right? Does it make sense?
Yes.
So, so you don't need to create as such. Operating system doesn't need to create as such. So those are that virtual address. Why we are referring that as virtual address? Because those addresses are not the real address. Okay, the address where that is actually loaded, that address is not exactly what processor is viewing. Okay, so that's why the name is virtual address. Does it make sense?
Yes, ma'am.
Okay. Okay, now the question is something like this. So let's say some virtual address you generated, means your processor has generated, which is outside the scope of the bound, I mean, out of the bound of your process, right? So then there is this hardware mechanism which will raise some exception. Operating system will get to know about this, that this exception has arisen. So now we need to do something. Means operating system should have one handler, means one piece of code, right? That code will handle if such events is occurring. Now what it should do? What do you think in such cases? What do you think? If such thing is happening? Yes.
Terminate.
Right. We should terminate. So operating system will terminate the process. It will remove the memory space occupied by the process. Means I'll just add the corresponding memory to the free list, right? Okay, good. So that's the thing which operating system should do in this moment. Okay, good. Right. So there should be, as in other words, there is one exception handler that operating system should provide, and if process tries to access memory outside its mount, then of course this is a hardware mechanism. CPU will generate some exception, and operating system will take action, right? In action, in the sense, it will terminate the process, right? And it will free the memory occupied by the process. Good. Now let us see this timeline to understand this in more detail. In more detail. So this type of timeline, I think you have seen it before. I hope you are already habituated with this timeline. So let us see this timeline once more. So this basically, here we have, in this timeline, here operating system, here we have hardware, and here we have the program. Okay. So at the initially when you are booting the machine, then of course it's done in the kernel mode, right? And as I mentioned in the last class also, we need to initialize the trap table, right? And trap table is basically in the hardware level. So what is trap table? So there basically you remember the address corresponding to system call, right? Time handler. Then with addition to that, today you have understood that we should have memory access handler, illegal memory access handler, right? So that exception handler, illegal memory access, right? So the thing which we had over here, that is actually illegal memory access handler. So that is also, there should be some code corresponding to that. So in the trap table, in the hardware level, so they should remember exactly which location this type of instruction are written, right? If you remember the trap table, which we mentioned in last class, right? There is one trap table which will give you the mapping of system call number, this illegal something, for example, memory access handler, right? Illegal instruction handler, all these instructions, they have some number, and corresponding to that number, in which address location it is stored in the physical memory, that mapping will be given. So that will be set at this moment, right? Then operating system will start the interrupt timer. I hope you have remembered what is interrupt timer we are talking about. That interrupt timer is going to play a vital role to take over the control, right? So we have so many processes are running, right? Operating system should take the charge sometime so that it can decide which process we should run, right? And if some process we should continue, right? This type of decision, if you want to have, then basically you should have some interrupter, right? That we also discussed in the last class. So operating system will start or initiate that interrupter, okay? And in the hardware level, after having this, then in the hardware level, the timer will be started, right? And it will start interrupting after let's say X millisecond, after each X millisecond, right? At the frequency of X millisecond, it will actually give you the interrupt, right? At the interval of X millisecond, sorry, not, at the interval of X millisecond, it will always raise one interrupt. Good. So that is the thing. Apart from that, of course, I hope you have understood that we have a list of process maintained by the operating system, right? So operating system should initialize that list, process list or process table, right? And with addition to that, which today we saw, that is basically important thing, is initialize the free list, right? It's corresponding to the memory, right? Corresponding to memory, we should memory management. You should actually have you should maintain a list corresponding to the memory which are available, right? So that list you should initialize. In other sense, initially we have all the things are free, right? So you just have one node correspondingly saying that okay, so the free is actually it is free from some location and to some other location, right? Initially you have that only. Good. Now operating system. So up to this, so far so all these things are actually done in kernel mode. Okay. Now let's say some user program comes into picture. So for that picture again, if we need to create the process first, right? So at the beginning again, that process creation is again done in the kernel level, right? Operating system will do that. So in other words, of course, it should allocate entry in the process table, right? In the process list you have. So there I should create one entry in that process table. Then we should allocate memory for the process, right? And you know that we have already discussed, we have base and bound register. We should set the base and bound register now. So base and bound registers are now hardware, right? So, right, then you return from the trap, means you move from the kernel mode, and now you want to move to the user mode so that the process can run, right? Does it make sense? So after doing this, basically what hardware is doing, hardware is basically restoring the registers of A, right? And of course, you need to change the user mode. That bit you need to change in the hardware level. And jump to the process A's program counter. That value means now you can fetch address and execute instruction. And we have already show you with example what is the meaning of fetch of some instruction. It involves basically translating some virtual address, right, to its actual physical address, and that will be done by hardware again. So here you have the hardware. If you want to fetch some instruction, so basically that virtual address location from where you want to fetch that instruction, that will be translated by hardware to perform the fetch correctly. Okay, does it make sense? And if some exception happens, right, then you need to raise exception also. So that part maybe with some example we have said here. Okay, let's say that there is no exception. So right, if we have some explicit load and store, then again we need to translate that virtual address to perform the actual load and store in the actual memory, right? Then also you need the help of this hardware, right? So in this way, this process will be, the process A will run, right? And maybe sometime again, due to maybe interrupt handler, this interrupt handler we had, which we actually initially initiated, right? So this interrupter, if it is, if due to the interrupter, again, operating system will get back the control, right? So in other sense, the trap will happen. And you know, during the trap means you want to context switch from process A to some other process B, right? Then what are the things you need to do? So all the things which you did earlier, that of course you will do. Addition to that, you are actually remembering the base and bound register of the process A, right? That you are going to remember, right? And for process, since you want to run the process B, for process B, basically, you just you just restore the value of base and bound register corresponding to the process B, which is stored in the proc structure of process B. You get those value, right? And you fill those value in the hardware level, right? You restore those registers of the process B, right? That is the additional thing which you are doing. Then you just make the change in the user, I mean, that mode bit you just change, right? The usual thing is now this process will be run, right? Now, if it happens that this process B executes some bad load, means it wants to write something to some address location which is out of its bound, right? So if that happens, then hardware will first raise some exception, right? Once that exception happens, then basically we need to move we need to change the bit from mode bit from user mode to kernel mode, right? So we are going back to the kernel mode, and jump to the trap handler corresponding to that exception. As I mentioned, that exception will also be, will get some number, and it will be corresponding code will be written somewhere, right? You jump over there and handle the trap. So handle the trap means here what you are going to do, you are, as we mentioned, you need to terminate the process, right? B, and deallocate B's memory, right? And of course you need to free the entry of B in the process list, right? These are the tasks which you need to do. Does it make sense? So in other words, this time line is very much important. I mean, at least if you want to understand what is happening, what the nitty-gritty is happening, then this is the best thing to learn. Means just this timeline will say you all the things. You don't need to do anything fancy. Okay, I hope you have understood all these things in details. Now let us see the simple thing which we implemented so far using base and bound register to translate virtual address to physical address. So what are the advantage of this, right? And what are the disadvantage? So as I mentioned, the advantage is basically it's very simple, right? You don't need to do anything fancy here. We just have two registers and adder, right? With that, you can manage this thing. So this is, in other words, very simple. And also it's fast. Why this is very fast? Because this address translation, whatever you are doing, this is in the hardware level. And hardwares are supposed to be very fast. Adder is very fast hardware. Comparator is also very fast. Registers, that is also fast. So in other words, the simple thing which we have implemented, base and bound method, it's very fast and it's very simple method, right? Now the question is, what are the disadvantages, right? That's the obvious question. Otherwise, we should continue with this simple thing. Why we are not going with this simple approach? Why we are going to think something different from this base and bound approach? So what do you think? What are the disadvantages of this? Any idea? Any idea? Any answer? If not, maybe let us see what are the disadvantages. Okay, so first disadvantage is, of course, it might happen that accidentally some program is overwriting its own code. There is no mechanism to stop, right? Did I say that we only check the bound, right? If it is within the bound, it can do anything. It can even change its own code. It can accidentally overwrite its own code also. There is no mechanism to check, stop this. Okay. And another important drawback is we are not permitting that some code or data of a process can be shared by other process also. It might happen that, for example, if I have a process right now, if you are creating one child process, right, by using for, so initially the whole address space of a child process is going to be same with its parent, right? But there is no such mechanism so that the child process can inherit or share the code part or data part, right, of the process, right? There is no mechanism in this simple approach. We don't have such thing, right? We need to think something differently, that's why. Okay, another thing is basically, we just assume that every process has same part, same size, right? So if you assume that, it is not realistic, right? Assumption. For example, I might have the stack and heap part of the process. It might need more space, right? But you are actually restricting that. As long, I mean, as you are saying that each process has same size of address space, right? You are restricting that. In other words, the process can't grow as it is as it needed, right? So this is also another restriction. So we need to think that this should not be the case, right? We need to modify our mechanism, in other words, right? So that process can grow as it needs, right? And another important thing is basically, it's since you think that all the processes are actually are of same size, right, or same size memory is needed, but it is not the case. Some of the process will need more memory. Some of the process will actually require very small amount of memory, right? So if you need more memory, then this is happening. This is the problem. And if you need small memory, then actually you are actually wasting your space, right? So for example, this internal fragmentation, this is one phenomena which it will happen. So what is that? It might happen that you can see all the processes are not going to take the full address space, right? Some of them are going to take small amount of space, whatever it is allocated to. So there will be several free spaces available within each memory of corresponding process. For example, here maybe there also some part is free, right? But since your approach or the method of handling this was like this, you need a contiguous part of your memory free to allocate some process, right? So it might happen that for a process, for a newly created process, you need, let's say, 100 MB of memory, right? And you did not find out 100 MB of memory free in a contiguous fashion. Okay, they are actually here and there inside some processes. In your total physical memory, there are actually more than 100 memory is 100 more than 100 MB is free. Okay, maybe 200 MB is free, but they are not contiguous. Here and there, they are actually fragmented. Okay, so this is a problem. This is known as internal fragmentation. Okay, so in other words, if you just add up those free memory, it is bigger than the requirement. But since your approach is to allocate one contiguous part of the memory to a process, you will not be able to allocate some memory to the process, right? The required memory to the process. So it's wastage of memory in other sense, right? So this phenomena is known as internal fragmentation, and which is a problem of, which is disadvantage of the simple base and bound approach. Okay, does it make sense? So these are the cones. So in other words, the base and bound approach is very simple approach. We have, with this simple approach, at least we have understood what are the objectives you have if you are going to manage your memory, right? And we start with some of the problems or disadvantages which we should take care, right? In next class onwards, we will see how to basically overcome these disadvantages. Okay, for example, how will you overcome that your program should not accidentally overwrite your own code. Okay, how you should manage that code sharing should happen, right? You should allow to share the code in between processes, right? So this also should be there. We'll see how to do this, how to manage memory in what should I say, in beautiful manner, so that you have less amount of internal fragmentation. Okay, it might not be always possible to get out of internal fragmentation totally, right? So here and there we might have small amount of free spaces. You can't avoid it totally, sometime, right? But you can minimize it, right? So we'll see in detail how to handle that in next class. Okay. So do you have any question? Do you have any question? No question? Okay. If not, maybe we can conclude. But before that, I think, okay, let me find out. Akshay mailed me some of the questions. So maybe I can just we can have a look at what he has in mind. Okay, maybe what I can do for that, I'll just, so, right.